the imul and idiv instructions. Imul and idiv are the sign-aware versions of mul and div. Those two instructions understand the 2's complement representation. How do these instructions work, or at least what result should one expect? One can think of those instructions as doing the following. First, we remember the original signs of the operands. Maybe we multiply positive times negative, or maybe negative times negative. We first remember the original signs. Next, we convert all the numbers to positive numbers. How can we do it? Using the 2's complement inverse method. Next, we invoke the operation. For example, it could be multiplication or division. And finally, we convert the result to negative if necessary. For example, if we want to multiply positive times negative, we take the negative number, we change it into a positive number, then we multiply, and finally we change the result back to be negative. This is how you can think about what those instructions do. It could help you predict the result as you use those instructions. I have to tell you that this is just a way of thinking about what those instructions actually do, though I'm not sure that this is the way that they are implemented. Maybe the engineers or the guys that work on the processor found out some other faster way to make it happen. But as a general rule, this is the result that you should expect from these instructions. You should be able to predict the results using this kind of thinking. Let's look at another example, this time about division. I'm going to show you an example in the 8-bit 2's complement, just because the 32 bits is pretty long and it won't fit inside the screen. We want to solve this. F8 divided by 4. We can see that this kind of division is negative divided by positive, because this number is negative in the 8-bit 2's complement representation. We actually already know that we expect a negative result. Let's take this number, F8, and convert it into a positive number, so we can do the division. We get that F8 is represented this way in binary. Then we flip all the bits and add 1. This is the 2's complement negation process. And finally we get this number, which is just 8. So actually F8 in base 16 in the 2's complement representation, it actually represents -8. Now we can just divide 8 by 4 and we get 2. And we can conclude that F8 divided by 4 equals -2. Now we want to represent the result in the 2's complement representation. So first we check out the binary representation of 2, which is just 10. Then we flip all the bits and add 1, and we get this number, which equals Fe. So finally, the result of this division, F8 divided by 4, should be Fe. I should discuss maybe a bit each of those instructions, imul and idiv, although there is not much to talk about, so I'm going to do it pretty fast. Imul is about signed multiplication. It has a signature mostly like the mul instruction, something like this. It has one argument, and this argument is going to be multiplied with the relevant part of of EAX, maybe with AX or maybe with AL. It depends on the size of the argument. Just like in the mul instruction, there are a few options. If the argument is of size 32 bits, then this is what is going to happen. EAX is multiplied by the argument, and the result is put inside EDX EAX. If argument is of size 16 bits, then AX is multiplied by the argument, and the result is put here, in DX AX. If the argument is of size 8 bits, then AL is multiplied by the argument, and the result is put in AX. It was mentioning that IMUL has some more advanced forms. I think that some forms of IMUL actually have 3 arguments. You might want to use it at some point, and maybe we are going to see these forms in the future. You can look it up yourself to check it. Let's look at some example. We put the number 9C inside AL and the number 19 inside CL. I remind you that this number is negative. You can check it out yourself that this number is actually minus 64 in base 16. Now we multiply those two numbers. We get the result inside AX as expected, and we get this result. Just to make sure that it went right and that we understand everything, let's check it out ourselves. We move to hex, and also we move to word size calculation. We only want to have 2 bytes. Let's calculate. We multiply 64, because as we said before, we first move everything to be positive and only later we deal with the signs. So we have 64 times 19, and we get this number, 9C4, which is actually this number. But if we inverse this number, inverse it relating to the sign, we are going to get this number. We can also do this in the calculator, using this button, the plus minus button. We can see that we actually got the wanted result, F6-3C, which is what is expected to be inside AX after this calculation. The IDIV instruction. The IDIV is pretty much like the div instruction. The only difference is that it understands signs. It understands the signs of all the arguments. It also has 3 forms, and maybe even 4 forms if you work in the 64-bit long mode. Let's talk about those shortly. This is pretty much the same as the div instruction, so I don't want to speak about it too much. In the first form, we divide EDX EAX by R, and the result is put inside EAX. By result I mean the quotient. The remainder of this division is put inside EDX. If the argument is of size 16 bits, then the quotient of DX AX divided by arg is stored inside AX, and the remainder is stored inside DX. For the case of 8 bits, we have that AX is divided by argument, and the quotient is stored inside AL. The remainder is stored in the higher part, inside AH. Let's look at the following example, which is mostly like the example we had earlier. It is just upside down. Maybe you remember, let's take a look back. Here we multiply those two numbers, 9C and 19, and we get this number, F6-3C. This time, we divide this number, F6-3C by 19. And we actually expect to get the original number, 9C. I picked to do the opposite example just so you don't have to calculate everything again and you can understand what is supposed to be happening. So this number is first converted into its positive form. This is how you can think about it. It probably doesn't work this way inside the processor because maybe the processor does it in some more efficient way. But when you think about it yourself, this is a good idea to first convert everything to positive. So this number actually means 9C4 when positive. And then we divide this number 9C4 by 19. And we are going to get this result, 64. Then we just turn it back into negative. And we get the number 9C. AH is going to contain 0 because the remainder was just 0. We know that the remainder is supposed to be 0 because this number is the multiplication, the exact multiplication of those two numbers, of 19 and 9C. We have seen it in the previous example, in the previous slide. Let's look at an example of combining iDiv and CDQ. This is very common. You are going to see this a lot, and I also hope that if you are going to use the iDiv instruction, you will consider using CDQ yourself, because they work together pretty well. Those two instructions are really friends, you might say. Let's look at what we have. We first move 3 into ESI, then we read some number as input, using this subroutine, read hex. Then we extend the input to be both in EDX, EAX. It sign extends the input. The original input was just inside EAX, which is of size 32 bits, and we want to extend it to 64 bits to be inside EDX, EAX. After we extended it, we can divide it by 3. And finally, as we get the result inside EAX, we print it. We print it back to the console. The important part of this example is this combination, the CDQ and iDiv, which is pretty important. Sometimes you can see code of people that just began programming in assembly, and if they don't know about CDQ, then they are going to try to extend the input using maybe the move EDX 0 instruction. But if you do use this instruction instead of CDQ, you will not get correct results for negative inputs. You want to be able to deal with negative inputs too. Maybe if someone gives you -6, you want to get a result of -2. But if you extend using move EDX 0, the results you are going to get will be sometimes wrong. They will be wrong when the input is negative. Summary. The neg instruction can find the 2's complement of a number. We can extend numbers using the move 0 extension for the unsigned case and move sign extension for the signed case. We could also extend numbers a bit differently, in place. Maybe using one of CBW or CWDE if we want to extend our number only inside EAX, or maybe using CWD or CDQ if we want to extend to EDX2. If our number is inside EAX and we want to extend it to EDX, EAX. The imul and iDiv instructions are the signed versions of the mul and the div instructions. The CDQ and iDiv instructions work pretty well together, as we have seen in the last example. exercise. We have learned about many new instructions, and this time doing exercises is pretty important. You are going to have some code reading, where you will see some sign-aware instructions that we have just learned about, and also some code writing, so you can check out the new instructions that you have learned and maybe try to use them in different ways. Have fun! See you next time.